All right, everybody, good morning. We've got a couple of things to just go over quickly here before we get started on the next lesson. I want to back up to the problems dealing with vertical circular motion that I had asked you to keep on top of, and I realize that some of you may not have completed them all, but before we go on, I do want to give you the opportunity to ask questions regarding vertical circular motion. This is on page 17 of your unit handout, and again, I kind of gave you a shortcut here. I don't want to eat up part of today's class time explaining where the shortcut comes from in terms of a free body diagram. I just want to say to you that when you have, say, an object on a piece of string that's twirled in a vertical circular motion, that the tension which is the applied force by the string to the object, is different at the top than at the bottom. And it can always be found by taking the net force and adding or subtracting the force due to gravity. And what I'm about to show you is a little bit of a shortcut, but it comes about from free body diagrams. It's the one area in this whole course where I think going back to a free body diagram each time is confusing for students. We just use our knowledge that while this object is in a circular orbit vertically, when it's at the top, the tension will be less. Because when it's at the top, you're trying to pull it down towards the center to keep it in orbit, but gravity is already doing part of that for you. So when it's at the top, of the orbit, you're going to use the minus but when it's at the bottom, you're going to use plus, because when it's at the bottom, you're trying to pull it up to get it to curve upwards, so you're applying a force towards the center, which is above where the object is. You're trying to pull it up, but gravity is hindering you. Gravity is fighting you, so you got to apply that extra force of gravity just to break even. Then you can worry about forcing it up to cause it to move with the required net force. So does anybody have, and by the way, should just end it there. This is equal to ma, which is centripetal, and the centripetal acceleration is v squared over r, or this is equal to ma, which is centripetal, and the centripetal acceleration is 4 pi squared r over t squared. It's not very often that we go that route. I would suspect that for this question we're looking at here, when you completed it, you used mv squared over r in conjunction with this. And I think, Jordan, we were talking about this one yesterday, weren't we? So you had to calculate the speed first to use v squared over r. I didn't mention it to you, Jordan, but you didn't have to calculate the speed. You could have just put the period and the radius into this beast on the right. Mass times 4 pi squared mr, 4 pi squared r over t squared. So this is it. This is what you do for vertical circular motion. Can you take a look at your work, please? If you have any questions, now would be the time to go over them. Yeah.
Could you do number 4?
Certainly. I'm just going to wait for my computer. There we go. Number 4. So driving in your car with a constant speed, you drive over a hill that has a vertical circular radius. And we want to know the apparent weight of a 75 kilogram person that's in the car as you pass over the hill. I don't know if you've ever experienced this. I grew up in North Edmonton, and there was a neighborhood, Clairview was the neighborhood. And there was a portion of the road, it was, I think, a defect in the engineering, and it was there for a lot of years. And I've been back and they've fixed it. We called it the Clairview Hump. It was this big bow in the road that came up. And we would drive over it fairly fast because when you drove over it, you would feel lighter. We never drove over it fast enough to get air, but you would notice that you were lighter. Okay? And remember that when we talk about the net force in terms of circular motion, this is also called the centripetal force. And when we talk for circular motion about the applied force, we often call this the force of tension, right? So I'm talking about the net force and the centripetal force being the same thing. And over here I'm saying the applied force is also the force of tension. But you might remember that when I went through the review here, I said, I'm going to call this the force of tension because it's the tension in a string. There's no string here. So the applied force is the force of the car seat pushing against you, or of you pushing against the car seat. We don't want to really dwell too much on Newton's third law, but the bottom line is that this is the normal force. And this actually goes back to Unit 2 when we talked about apparent weight in an elevator. And we said that when an elevator is accelerating up or down, or maybe it's not accelerating, it's the applied upward force on the elevator that is your apparent weight. And we translated that to a tension in the cable because that was what was supplying the force. Here, there's no cable, but we can still call it the applied force. It's just the normal force. All that being said, what I'm getting at is this is your apparent weight. Not only is the F the applied force, but it's also your apparent weight in terms of how you interpret it. So you are going over the top of a hill, which is the top of a circle, which means that the applied force will be equal to the net force minus the force due to gravity. Because at the top, there's less tension, you will feel less weight. And it occurs to me I may have made a little mistake here, back here. I did, and it's minor. I think nobody would have noticed it, but it is nonetheless a mistake. Right? We're talking about adding or subtracting the magnitudes. So that's what I have written here for number 4. I just didn't put the absolute value signs. Again, I want everybody to know, I guess it's this important that I repeat myself with this idea again and again, that this is the same as that. They mean the same thing. So regardless of how you do it. So that means I can take MA, which is centripetal, minus mg, and then I can say m times v squared over r minus mg. And I suspect, Christina, you and many other people would probably just be content with doing that. You don't need to go MA. You cannot cancel the masses because we want to know what this is equal to. This is a force. And if you divide everything by the masses, you're not finding a force. You're finding maybe kind of the g acceleration that you would experience, but that's not what we're after. We're after the actual force. Do we know the speed? 12, and the radius is 35. You know, it's not a circle, but it's a road that has a circular portion to it. So we can put in the mass, which is 75 kg, multiplied by, I think the speed I saw was 12, squared over the radius is 35, minus 75 times 9.81. Now here's an interesting thing. Well, I'm interested by it. Let's calculate the answer, and then I'll tell you what's interesting. So can you do me a favor and run those numbers through your calculator? So what do we have? 75 times 12 squared, which is 144, divided by 35, minus 75 times 9.81. Is that what you get? Wow. I've subtracted the wrong way. And boy, this is going to be tough for me to explain. Huh. I've subtracted the wrong way. But I don't want you to think that I've got this stuff backwards. I don't. This would be true, and before I explain why we have to subtract the other way in this example, let me be clear. I would never ask you this on an exam, okay? But I think it's an interesting idea. The reason why it's like this for an object on a string or for an object going around a circular track is that the object is inside of the arc and is being pulled by something inside. But what's happening here is you were on the outside of the curve and you were traveling along the outside. So you have to subtract the opposite way. If we would have done all of this with free body diagrams, your free body diagrams would lead you to this conclusion here, and down here, they would lead you to this conclusion. And clearly, if you subtract the other way, you won't get negative 427, you're going to get positive. I'm just going to roll around in my head whether it's worth the time for me to show you the free body diagram here. So give me 1 second. I can, okay, and it's not a difficult thing. Why not? Why not? For a ball on a string, when it's at the top, when it is at the top, and there's a piece of string pulling it in, there is an applied force down and there is a force of gravity down. Right? And this is going to show us that at the top it's going to be the magnitude of the net force minus the magnitude of the force of gravity equals the applied force. How is that going to show it to us? The net force has a magnitude that will be equal to the sum of these two magnitudes. Because look at the diagram. They're in the same direction. Okay. And that means the applied force will be equal to the net force minus the magnitude of the force of gravity. At the top, we subtract. So why is it that at the top of the circular road we subtract, but we subtract the other way? Well, here is the road. So that arc is circular. Here's the car. Now, the car is on the road, right? which means that there has to be a net force downward. Now, there is a normal force. I just want to straighten this out. It doesn't matter. Yeah, I'll straighten it out. There is a normal force, which is up, which is your apparent weight. The normal force is your apparent weight. This is our goal. This is the answer to the question. And there is a force of gravity that is acting down. So, look at this now. When you look at the top of an object on a string, both forces are down. But when you look at the top when an object is outside of the circle, one force is down and one force is up. And by the way, you could never talk about this being on the outside of the circle at the bottom, because then, well, that doesn't make sense. You don't, unless you're in Australia. And that's a joke. You wouldn't change it around if you're in Australia. So now what happens is the net force, I don't even know if this is going to work, will be equal to the force of gravity. That's still going to give me the same thing, I think. Minus, no, the normal force. It's going to work. So we're trying to, do you agree that this is what you would do to the magnitudes to find the net force? So now I want to find the normal force. It's negative. I'm going to move it over here, and it's going to be Fg minus F net. And when you look at an object on a string, it's F net minus Fg. So, excuse me for 1 minute. No, that's all right. Good morning. So, the point I want to make here is that's the explanation for why we have to subtract in the opposite order. But I think, and I believe it's important that you can follow that, because many of you will go on to post-secondary and take physics. I mean, you guys have good memories. Your brains are still young. You remember these little details. You might be sitting in a introductory physics course in university, and the prof does this, and you go, oh, wait a minute, oh yeah, I remember seeing that. But I don't think I would ask you to analyze it this way on an exam. I would limit anything in this course that I evaluate you on with vertical circular motion to objects that are on a string, or to objects that are inside, like a car going through a vertical circular road, but not going on the outside. So that's why when we subtracted, or when I subtracted, I got a negative. I had one more thing I was going to say to you, and now I feel as though, well, let's say we did it the proper way, okay? We took the mass times 9.81, and we subtracted the mass times v squared divided by r. I think I've got all those numbers right. Okay, so let's say we do it the proper way. And you subtract it the way it should be subtracted. And this is more elective material, which means you don't need to know this. But what I find interesting is if you did this correctly and you got a negative, what would that tell you? You know? No, it wouldn't actually. You know what it would tell you? It would tell you that the force of gravity is less than the normal force, which would mean you're getting air. You've reduced the normal force to zero. So what we could do is figure out how fast you'd have to be moving to do that. And I'll just do the calculation for you. Can you take 35 times 9.81 and then take the square root? So what I'm doing here is I'm saying if you lose contact with the road, you are weightless, which means mv squared over r equals mg. So r times g, take the square root, and you get what?
18.5.
Okay, so it's pretty close. Like 12 meters per second to 18 meters per second isn't that much faster. So at about 18 meters per second, you would start to leave the seat as the car went over the hill. Anyway, does that help? Okay, other questions? Yeah.
Can you do
Number one? Certainly. So we have an option here with number one, Faye. I've already gone through this whole idea, and I'm going to erase all of this and just talk about the basic idea that at the top, we're going to use the net force minus the magnitude of the force of gravity, and you understand that. Okay. And the net force is ma, and the force of gravity is mg, and the acceleration due to gravity, or the acceleration of the object, is a centripetal acceleration. So you have two options here. You could do this, and then stop and say to yourself, okay, I know the mass, I know the radius, I think. Yep. I do not know the speed. Okay? So your secondary goal here, or I guess maybe your primary goal at this point, is to determine the speed. And the speed is 2 times pi times the radius divided by the period, which is the time for one full revolution. This goes back to the very beginning of the unit, Monday of last week. So we can put in 2 times pi times 0.93 meters divided by the period, but we don't know the period. The period is how many seconds it takes to go around once. However, we do know the frequency. The frequency is 4 hertz. Revolutions per second means hertz. And we also know from our formula sheet that the period is the reciprocal of the frequency. So if we take our calculator right now and go 1 divided by 4 and get 0.25, that means that the period is 0.25 seconds. I left the units out for the distance, for the radius. I'll leave them out for that as well. So now what we can do, and I'm going to finish the rest of this question on my calculator rather than writing a bunch of stuff, is I can take 2 times pi times the radius of 0.93 divided by 0.25, and this is the speed. And now I can take mv squared over r minus mg. Was it 130 grams? Is that what I saw? Which is 0.13 kilograms times this speed squared divided by the radius of 0.93 minus 0.13 kilograms multiplied by 9.81. So you get 75 newtons. Is that the answer to A? I hope. It's not.
That's the answer to B.
Oh, I did B. Right, I was looking at the top. I saw at the top. I didn't see it was B. This is B. At the bottom, which is A, then we would add that mg. The reason, I don't know if it's worth talking about, but why not? We're here. The reason why these two are very similar is I don't believe the force of gravity is very large here compared to mv squared over r. Like, mv squared over r is 13 times, or 0.13. 0.13 multiplied by, what was that, 23.37 squared divided by 0.93. It's 76 newtons of net force. And that plus or minus mg, well, the mg is this. It's pretty thin, right? So there's not a lot of difference in the tension at the top and the bottom. The other thing I was going to say is, instead of doing this, you could do the following. Acceleration, when you look at your formula sheet, it says centripetal acceleration equals v squared over r equals 4 pi squared r over t squared. So you could use 4 pi squared r over t squared instead. You still have to find the period using this, but you will get the same answer. Other questions? Yep. Yep. So this is on the outside. This is on the outside. But because we're asking for that tipping point where you feel weightless, it shouldn't matter. Because if you feel weightless, that means the applied force must be equal to 0. And if you were in an elevator and you felt weightless, then the applied force upward is 0, and the whole elevator and you are in free fall. Which means if you were in an elevator and you feel weightless, the only force doing anything is the force of gravity. And the same thing is true here. We can say that this net force is really just going to be provided by the force of gravity. And whether we put vector symbols on this and talk about forces with direction, or whether we put absolute values, doesn't matter, because at this point in time, this is the only force that's acting on you. So it's the net force. That means MA equals mg, which means v squared over r equals g. And this would be the result whether you were weightless on the inside of a curve or the outside. It's not going to matter. It's also interesting because if you're in a car with 3 other people, you're all going to feel weightless at this point in time because your masses don't determine that speed. So all I have to do is, I would prefer to do this. Just be careful to make sure that you have a radius and not a diameter. So you have to take 39 times 9.81 and take the square root. Let's see what we get. So about 20 meters per second, which is scary fast on a roller coaster anyway. I mean, you multiply that by 3.6, I think you get 72 kilometers per hour. The hair is really blowing your hair, the wind's really blowing your hair back.